This is a demonstration of arithmetic functions in the SCC single cycle computer. So I've opened viciLab and I'm running from the design library and opening up add, add invert, decrement, increment, add increment, subtract and add immediate. This is a set of views or tabs of the behaviour of arithmetic functions within the SCC. It will take a few moments to open and to request your username and password. So enter the password to configure a system on chip on the viciLogic hardware array in the cloud. And when this widget appears, you have access to lots of tabs with logic specific to the instruction that will be operating. Open up the add, addinv, etc. named program in the individual instructions folder. This is an assembly program. It has a main section and a setup section. In the main program, it calls the setup function, which puts value 238 in register 4 and 107 in register 1, and then uses 1 and 4 in a series of arithmetic functions in sequence here. So let me assemble the program and transfer the program to program memory. So the series of instructions are shown in the IDE here, and the tab related to the current instruction is shown on the right hand side. So the first is the call. That's dealt with in a different video, so I'm simply going to step through from the call function to run the subroutine and to return from the subroutine. And that will have set up registers R1 and R4 with value 107 and 238 respectively. Now I add R1 and R4, put the result in R2. The add instruction has two parameters, or two values coming in from the operand fetch, using RIA, this field, bits 5 to 3 in the instruction, defining register 4 as a source, and the value 238 is provided into the function execution unit. And RIB provides register 1 on bus B, 107, into the function execution unit. Within the function execution unit, the two signals ALU function are 0 and 1, and the default path through the function unit is the arithmetic unit, so there's no additional signals that are driving multiplex or path selects within the function execution unit. And the 0, 1 code on ALU function selects A plus B as F unit out. So 238 is added to 107 to get 33F. The destination register is register 2, as is seen over here, and the field here is 8 to 6 in the instruction register. The opcode is here. This writes into the registers with the red box indicates that this is the active register bank. Register write is asserted in the instruction decoder, and it will write to register 2. The program counter will increment. So as I single step, the value now in register 2 is 33F. Now I have different instruction, same destination, same source parameters 4 and 1. This time RFC in is a 0, ALU function is 10, and that selects A plus not B, and the answer is 130. That's again written to register 2, and the answer is 130. You can see that over here as well. Then there's a decrement, which takes register 4, decrements by 1, and writes the result to R2. So register 4, a single source, bits 2 to 0 of the instruction are not used. The value is 238 from register 4 through the function execution unit. 1, 1 on ALU function with arithc in 0. Subtracts 1 from A, gives 237. And again, that will be written to the same destination address. And meanwhile, the program counter simply increments at register write is asserted. Step again. Now I'm incrementing R4 to give it R2 result. 238 will become 239. RC in now is a 1, and ALU function 0 and 0. This is a mistake in the text in the picture. That should be a 100 for an increment. I'll correct that. And I step again. This time I have an add plus an increment. So previously I added R4 at R1, and now I increment that by 1. RFC in is a 1, as before, in 0, 1, and ALU function selects A plus B plus 1. Same destination, and I step again, and the answer was 340. Now I subtract R1 from R4 and put the answer in 2. So 107 from 238, which gives 131, and I put the answer in 2. So RC and ALU function combination is 110. And step 131 is in R2 here also. And the last one is add immediate. Add immediate is a little bit different in that the output destination is 2 as before, RIA is 4, and it selects register 4 having been fed back through this multiplexer based on these 3 bits. But the instruction decoder also asserts a signal called cell ADI-DAT, and that selects onto the B bus the value instruction 2 to 0. Those 3 bits, 1, 1, 1, they're currently 7. I'm adding 7 to register 4. And I pad that with 13 zeros to make it a 16-bit value. You can see the value 7 is on B. And I add 238 to 007, gives me 23F. The RC in ALU function is the add as before. And the only difference now is that rather than A and selecting B as a register input, it's selecting B as the 3 bits of the instruction. And as a step, 23F is written to register 2. And that's the end of this program, and now it will hold the PC as other programs have done because end program is asserted in the instruction decoder. So let me reset the program now and go back to the call function and step to the end of the function call into the add instruction, and let me look a little bit more detail in the function execution unit. So this is the function now that is selected. The output of arith unit is selected through here, here, and here. These muxes select the path through when there are zeros, as in their default values. So if the instruction decoder does not assert these 3 signals, which would be their default values, then the default path in the function execution unit is arith unit through to F unit out. In this particular case now you can see the 238 and the 107, 238 and 107 registers 4 and registers 1. And the output of the arithmetic, which is add, is shown here, and it's selected through this path. The operand fetch has register coming through here to give 238 on A and 107 on B. And so let me step one more into add invert. In this case, I can go to the function execution unit, and again this passes through, but I can open up the arithmetic unit and see the detail in here. And the path through is shown as before, the default path with all of these signals from the instruction decoder deasserted, and the 010 will give add and invert. A added with not B. Step again and enter the function execution unit and the internal logic of the arith unit, and in this case I'm decrementing. You can see that the only change is this table for the combination of inputs RC in and ALU, the output is A minus 1 in this case. The increment, and in this case RC in is a 1, and 0, 0 will be add plus 1. So that's the end of the demo.